Here's a circuit and we want to solve for the current. So let's apply Faraday's law. The left-hand side is the integral of E dot dl around our circuit. So going through the power supply we have minus 2 volts when we integrate E dot dl, and through the resistor we have plus I times 2 ohms. This is going to equal minus the change in flux linkage with respect to time, but since this is a DC circuit, nothing is changing with time, so that's equal to 0. So we have 1 amp flowing. So here's another circuit, and again we want to solve for the current, so let's apply Faraday's law. Integrating E dot dl around our circuit, we have minus 2 cosine of 3t plus I times 2 ohms. Since the current will be changing with time, you'll have a magnetic flux through the surface of our circuit that's changing with respect to time. So you will have a term here on the right-hand side. If the frequency is low or the surface area here is small, you could approximate this as 0. If these wires are long and the frequency is high enough, this can become a significant term, and we have to treat this as a transmission line. Let's look at a circuit where we now have an inductor included. We have a power supply, a resistor, and an inductor with the switch that will close at t equals 0. You know the current will build up to a value of the power supply over the resistance of the circuit. Let's apply Faraday's law. So we'll first integrate E dot dl around our circuit. We go through the power supply, we get minus V. We go through the resistor, we get the current flowing through the resistor times the value of the resistance. Let's assume the inductor is made of a wire of very high conductivity. If you have a current flowing in the inductor, the current density in the inductor is sigma times E. So as sigma goes up, E goes down. So if the conductivity is high enough, the electric field is small enough that it will be negligible, so the integral of E dot dl through the wire making up the inductor we can approximate as 0. And that will equal minus the change in flux linkage with respect to time, so that will be the flux inside our circuit here, and also the flux linkage inside the inductor. In the inductor, the flux linkage is equal to the number of turns times the magnetic flux. And if you have a lot of turns, this term can dominate the total flux linkage in your circuit. So in other words, the flux linkage in the inductor will be much greater than the flux linkage through this surface of your circuit. So we'll approximate the change in flux linkage with respect to time as just that associated with our inductor. Now we will see why we define inductance as flux linkage over current. For lambda, I've now substituted the inductance of the inductor times the current flowing through the inductor. We know the inductance is a constant, so we can factor it out of our differentiation. Let's solve this equation for V. This equation should look familiar to you, which previously you would obtain using Kirchhoff's voltage law, and this term as the voltage associated with the inductor. But if the voltage is really the integral of E dot dl through the inductor, and the inductor has a negligible electric field in it, the voltage obtained by integrating E dot dl is really 0. This term really comes from Faraday's law and the change in flux linkage with respect to time associated with the inductor. We are now going to look at the energy associated with an inductor and the energy in magnetic fields. When an electron flows around this circuit, it delivers energy to the inductor and the resistor. The potential difference across the resistor and inductor is the amount of work it takes to move 1 coulomb of charge from the negative terminal to the positive terminal. So an electron flowing around the circuit will deliver an energy of E times V to the inductor and the resistor, where E is the magnitude of the charge on an electron, 1.6 times 10 to the minus 19 coulombs. If you take the current flowing around the circuit and divide by the charge on an electron, you obtain the number of electrons flowing around the circuit per second. If you take the number of electrons flowing around the circuit per second and multiply it by the amount of energy being delivered by each electron to the circuit, you obtain the energy being delivered per second, which is just the power, I times V. So after we throw this switch, the energy delivered to the resistor and inductor is the integral from 0 to t of the power dt. And for the power, we know it's the product of the current flowing and the value of our power supply. So for the voltage, let's insert this expression, which we obtained from Faraday's law. And now let me write this as two terms. This first term should be familiar. That's just the I squared R heating of the resistor. So this second term is the power being delivered to the inductor, so it will be the energy stored in our inductor. Let's focus on this term, the energy delivered to the inductor. So here's the calculation of the energy delivered to the inductor, and I've factored out the inductance because it's a constant. If we let t go to infinity, we know that the current flowing through the inductor will go to some final value, and let's just call that capital I. So the integral of I di will be I squared over 2, which will become 1/2 L I squared. So if we have a current I flowing in our inductor, the energy stored in the inductor is 1/2 Li squared. And we will now see that that energy is stored in the magnetic fields inside the inductor. Previously, we found the inductance of a coil of length L with N turns. Just to remind us, we applied Ampere's circuit law and we used an Amperian loop that went down the center of our coil. So the integral of H dot dl was H inside times L because we get negligible contribution to the integral of H dot dl on these three sides. And it was equal to the total current enclosed, which was the number of turns of our coil times the current flowing through our coil. So the magnetic field intensity inside our coil is Ni over L. So the magnetic flux density field inside the coil is the permeability of the material inside the coil times H inside the coil, with a cross-sectional area of the coil being S. The magnetic flux inside the coil is the magnetic flux density field inside the coil times that cross-sectional area S, or with this substitution for B, it is mu NIS over L. The flux linkage lambda is just the number of turns N times the flux psi inside the coil, which becomes mu N squared IS over L. The inductance of our coil is the flux linkage over the current, or mu N squared S over L. We know the energy stored in our inductor is 1/2 Li squared. So for our coil, Let's substitute for L this expression. And for I, looking back here, let's substitute LH over N. So squaring this, let's rewrite this as 1/2 mu times h squared. L squared over L gives us an L. We have an S, and we'll have an N squared over N squared that cancel. So L times S, the length of the coil times the cross-sectional area, is just the volume of the inductor. So this 1/2 mu h squared is the energy density inside the inductor, which I'll designate as lowercase w sub m. So the energy density in a magnetic field is 1/2 mu h squared. Now you might say there's energy outside the coil because you have a magnetic field, and that's true because for a finite coil like this value of H isn't accurate when you get near the edges of the coil where you start to have fringing fields. But let L get larger and larger, and as L goes to infinity, what you would see is that the magnetic field never comes outside, so this would be an accurate expression for the energy density. So here is a comparison between inductors and capacitors for the energy stored in an inductor and a capacitor, and here for the energy density in the magnetic field and an electric field. Since B is equal to mu h, another way we can write the energy density is 1/2 B times H.